Well, hello everybody, and thank you, Dan, for the invitation. I'll just fuel up here for when my voice is struggling. But as Dan mentioned, I would like to speak to you about additive manufacture from a design perspective and looking at the possibilities that we see come out of this new way of manufacturing. And the program for today is in these three parts. So a bit about the background for myself and the company and the products we have. And we have some on the 3D cooling concept, which I will tell you more about, and the LEDs we work with. And also the research projects we are involved in that also has topology optimization and what have led to them, and our thoughts on how to combine different functionalities in each part, getting the most out of additive manufacture, and how this can affect the supply chain. And then I would like to finish off with a future scenario on where we can see these things applied later on, and maybe with your help we can add some ideas to that, and then some questions. So who am I to talk about these things? As you can see, additive work in a voxel-based form started for me at the age of 4, and thank you to Lego. I think it's 10 years before Jørgen entered the business, but I'm still grateful for that kind of toys that inspires your creativity and get you to play with the ideas and test what works and what doesn't. And I think the same dynamics apply to additive manufacture. There's a lot of trial and error, and there's a lot of provoking the conventional way of thinking. Also, I'm one half of this AT Lighting, a small design and development company. Yes, technology enthusiast. Before lighting became a large part of our work, in 2005 I had the opportunity to work with the Danish loudspeaker company Audio Vector, designing a reference loudspeaker for them. It has a very low, what we call wife acceptance factor, but it plays fantastic music, and I'm still negotiating to get a pair, of a set of them, but they are priced at 146,000 euros a set. The Danish ambassador in Washington had more luck with his wife, so there's a set standing there. The next part is interior products of different sorts, but these two are loudspeakers made out of ceramics, trying to aim for a high wife acceptance factor. In the center we have this electronic water faucet with a user interface, a touch interface, where you have the cold and hot on the horizontal and the water flow on the vertical. So you would just have one pressure or one touch to activate, or gesture, or however, in this smart technology era. And it would be easy to clean, and all of these hygiene things we need to have in account as well. Then there's some lifestyle products. It's credit card cases. It's more of a gentleman's accessory in tune with cigarette cases as we knew them, but that's not so politically correct anymore. But that could be a way of thinking the next type of wallet. And then in 2009, this light bulb came along that started the AT Lighting fairy tale or adventure. And this is the company profile. We have these three main technologies that we built everything upon. And it came step by step. So what we learned from the light bulb, we applied to lamps, and then later on to these 3D cooling concepts. And on the right, you can get a sense of the design profile of the company. So that would be the background for me to talk about all of this. If we go into the LEDs, they are pretty cool, but they still emit a lot of heat. So in essence, the energy applied, 70% will be emitted as heat. But as opposed to incandescent light bulbs, it doesn't emit the heat in the light. It emits it like a CPU on the backside of the chip. And if you do not cool it, it will break down almost immediately, and we have tested. And on the other hand, if you cool it very well, they have a warranty of 50,000 hours. And if you have a lamp turned on 3 hours a day, that's nearly 50 years. So there's a huge span, and if you cool them poorly, they will have a poor lifespan. And also, the cooler the LED, the more light it emits while it's on. So it's crucial for this technology, and it's not always recognized by either the engineers or the consumers. So this would show a very basic way to look at a cooling system. We have the heat source in the bottom, an LED, but it could be a CPU or an engine or battery. We apply a material in the shape of a heat sink of some sort, and we can conduct the heat away from the heat source, and then there's an internal and an external geometry as noted here, but what I'm trying to get at is that the internal geometry is to get the thermal properties or the heat from the LEDs to be distributed evenly in the heat sink. Because as you can see in this part, it is hot in the center and it becomes more cold the further away you go. But this also means that when you go to the external geometry, you will have high performance close to the heat source and less heat emittance performance the further away you go. So if we can optimize the geometry for distributing evenly, we can activate the entire surface to the maximum and get a better performance. And in conventional products, if that doesn't do it, then you add a fan or heat pipes or some other technology to apply further cooling. This is our area, that's where we started on the geometrical side of this, and that's where additive manufacture plays a part. But before we got to that, we have this LED light bulb that set it all off. And if you look at this part, that's what we call the light engine. It is the base of the light source, and it's created like a chimney. And I actually have a small part here that you can view afterwards, but the chimney is made with LEDs on the outside and cooling fins on the inside. So what happens when the LED is starting to emit the heat? It gathers in the center and it creates a convection-driven airflow that then again creates a vacuum, getting cold air through from the bottom, and then we have a continuous airflow by natural convection without any fans or any energy consuming or noisy or fragile parts as well. And then to explain the product to you, then we have added a lens to this, because now we have a lighting profile that is horizontal and circular, but most lamps don't have this character or use of light, so we can add a lens to this, a ring that we apply on the outside, that would then again shape the light using acrylic lenses with total internal reflection. And then we can tailor-make the lenses for the lamp that they go into. And this is, for this Danish classic, they absorb 50% of the light from the light bulb you put into this. So if you look at the light bulb, it can be excellent, but the minute you put it into the lamp, you have to use a systems approach. So how much light are you getting out of this system with the light bulb and the lamp? And that's where the optimization for the optics come in. And this is also our first meeting with topology optimization, because this part here, this part here, that's a piece of software that has generated the design by using algorithms that creates the optimal shape for this. And we paid a note to this. It was a great way of working because we actually didn't have to do anything but to apply what we wanted. The functionality came out of the software, and we had a design we could manufacture. But using this type of this knowledge that we got from this, we went into designing lamps with integrated LED modules, and LEDs are directional as opposed to this incandescent sun that we have been used to. So we don't have to use a lampshade in the same manner as we did prior, but we still would like to keep an attachment to the iconic shape of a lamp. We met a lot of designers creating or designing lamps that looks like something that's going to the moon. It was a bit too drastic. We take one step at a time, also at the aesthetic point of this. So we changed the functionality of the lampshade into being a heatsink, a passive cooling device, and we could have a lot of material all of a sudden activated as cooling, and we get durability and a long lifespan and maximum light output from the LEDs. But the next job that we tried to manage was LED spotlights. But you can twist and turn these, and we started with the same way of using a chimney. But the minute you twist it, you want to light up your art on the wall, then you spoil the effect that the convection airflow has. And that led us to think, prior to this we had the two-dimensional lattice system from this lamp. Why not go into 3 dimensions? And additive manufacture was a gift for this. In the LED light bulbs we used plastics 3D printing for prototyping, and we also used it for investment casting for the heatsink. And now we had to go full scale. We could print these aluminium parts, and we had some funding for this and made some different geometries that were tested by the Technological Institute in Denmark. And what we learned was that we could get a heatsink that performed very well in every direction. And also what surprised us is these 3 in the bottom, they have the same mass properties, the same weight, but the one with the least amount of surface was the one with the best cooling performance. And that tells a bit about the design and what effect it has when using the conventional way of designing heatsinks. You could actually achieve a lot by going into the geometry and optimizing for the situation where the heatsink is used, instead of getting the conventional extruded and cast parts. So using these parts, we went into a collaboration with the Danish Technical University, who has a Topology division under their mechanics department. And we started making this. It runs in 3, and we have a design side that I'm responsible for, and there's a topology side, and then there is a software side to this. And we further improved and so on, but what is interesting here is that it's very time consuming to design these structures, and I think it's great fun, but being time consuming, it's not always good business, just spending hours in front of the computer. But this is the part, and what we're trying to achieve with the Hypercool project is that we would like to have a software that can take topology optimized structures directly into a CAD program like SolidWorks. So I could start off my work with the optimal functionality, and then I could apply my design constraints to this, how much space it can take up and so on. So somehow apply a design DNA to the topology optimization. So this would be an example of the work they do at the DTU. It's a researcher called Joe Alexanderson who made a code that also generates these heat sinks. This is a CPU cooler. It's made directional, so it's only to be oriented like you see in the picture. And what we have here on the left is the same optimization, but created in environments where we have viscosity like honey in the top left, and a viscosity like air in the bottom right. So that's the way the software and the optimization is differentiating depending on what the problem is. Yeah. What I want to get at is that it's easier to optimize in this honey velocity, and more complex because of the convection airflow. The multi-physics optimizations are extremely requires a lot of computational power. So at the moment it's very time consuming as well to use topology in this area of multi-physics, and we hope to apply some code that can do this faster, more efficient, and also together with the design constraints. So ideally we see this as an interplay between the optimization for functionality in the topology and optimization for additive manufacture, and then the overall design, the aesthetic optimization. And if we haven't got these into account, or the aesthetics, then I would say that I don't mind having these organic structures in satellites, but if it was something I should have in my house or somewhere where something we're seeing a lot, then it should have some aesthetic qualities and not only the functionality, because I think it would be a funny world if everything had these coral-like structures. And then the case that we're working on is we have this conventional way of doing an LED spot, and we have the AT lighting concept. And if we do a part-to-part assessment, then we have an extrusion of a heatsink that is, we have a slice of that, and we add it to a system. And on the other hand, we have a 3D printed heatsink. And if you look at the LED industry, then it's a blood red ocean market. It's a cost optimization game, so everything is to be done as cheap as possible, and additive manufacture isn't at the stage where you can call it cheap yet. But if you change your focus to a system to system assessment, then I think you could start to make sense of using additive manufacture. Because if you look at the supply chain and sourcing, shipping and warehousing, all of these issues, then you can go from this conventional 11-part spot assembled by 16 screws, I think, and with a fan and so on. And on the other hand, you can design two parts that clicks together with an LED and a conventional optics, and then you would have a way simpler product. And these are the dynamics that we are looking for and working with, because it brings some opportunities when you're not looking at the part itself, because you can all of a sudden start to do the math when you take out all of these, when you take out creating molds and so on for this, and then you all of a sudden have you can start a manufacture way quicker. You're less vulnerable, because you have essentially all the parts you need. You have the powder and you have the LEDs, and instead of these, if we lack one part in this, if there's a quality issue with the last shipment of one of these, then we can't get our product to the market. So that would be the part on the additive manufacture and our view of this. And going into the final part, the question would be, where could we apply this in other types of products or industry sectors? And for one, we have been thinking about these aluminium body Mac computers. They mill them out at the moment. It looks very fancy and it's a real nice tool, but the next natural step must be additive manufacture. And why not think and integrate some more functionalities into the chassis or the housing of the computer itself. And you might even think the brackets and everything into this and getting the same advantages as we saw from the LED spotlight concept. So the next part we are working with at the moment is this type of inverse system. You could start using this for water systems as well. So getting the heat out of water, and then again you could add the lattice system on the outside as well. So you could create systems for this, and you could also start. I would like to make an update of this structure, but what I want to illustrate with it is that if we make hollow structures, then we can start adding functionalities as you find in heat pipes. So you can add vapor chambers, so you can get heat away from the critical point immediately and then get it out to these tentacles or further away in the geometries, and then have an optimization by doing that. And you can even have weight savings and so on by doing this. And all of these lattice structures are, in our point of view, something you can use also in the structures of the component. You can get stiffness, lightness. If you work in the automotive industry, you could have collision zones that absorbs energy, or any kind we see a lot of possibilities, and I hope that this could inspire you to see a lot more. But this was the presentation I have for you today, and I hope you enjoyed it. I brought this from Apple, being a bit crazy, as I think additive industry is. I love the ambition of having a fully automated system. I love the fact that it's going from rapid prototyping to a real manufacturing system. So I'm also very glad to be here today and participate in the conference, but that was the work for me for today.